In this research paper titled PatientDx, Merging Large Language Models for Protecting Data Privacy in Healthcare, the authors address a critical challenge in using artificial intelligence for medical applications. Large language models, or LLMs, are powerful AI systems trained on vast amounts of data to perform tasks like understanding and generating text. These models, such as PaLM or MedPaLM, often have billions of parameters and are fine-tuned on specific datasets to improve their performance on tasks like predicting patient outcomes. However, fine-tuning these models requires training on sensitive data, such as patient records from electronic health records or medical reports. This practice raises significant privacy concerns because it can lead to data leaks, where private information might be inadvertently exposed through techniques like membership inference attacks or data extraction methods. In healthcare, this is especially problematic due to the highly personal and confidential nature of medical data. The paper introduces a new framework called PatientDx, which aims to create effective LLMs for health-related predictive tasks without the need for fine-tuning on actual patient data. Instead, PatientDx relies on a technique known as model merging. Model merging involves combining the parameters from multiple pre-trained LLMs to form a new model that inherits the strengths of the originals. This approach, based on recent advancements in the field, allows for better performance and generalization across tasks without directly exposing or training on private datasets. At the heart of PatientDx is a strategy that optimizes a building block merging process. The framework starts with a pivotal model that's already adapted for numerical reasoning, which is crucial for tasks like predicting mortality rates. Then, it tunes certain hyperparameters using example data based on performance metrics, but importantly, this tuning doesn't involve actual training of the LLM on the sensitive data itself. This means the process avoids the risks associated with fine-tuning while still enhancing the model's capabilities. To evaluate PatientDx, the authors conducted experiments using the MIMIC-IV dataset, which is a large, publicly available collection of de-identified health records from intensive care units. They focused on mortality prediction tasks, where the goal is to forecast whether a patient might pass away based on their medical data. The results showed improvements of up to 7% in terms of AUROC, which is a common metric for evaluating the accuracy of predictive models in binary classification tasks like this one. AUROC measures how well a model distinguishes between positive and negative outcomes, so a higher score indicates better performance. When compared to models that were fine-tuned directly on the data, PatientDx demonstrated that it is less susceptible to data leak problems. This is a key advantage because fine-tuned models can sometimes memorize or retain fragments of the training data, making them vulnerable to privacy attacks. In contrast, the merged models in PatientDx maintain strong performance levels without this risk, making them a safer option for real-world healthcare applications. The authors also explored the qualitative aspects of their framework through a case study. This involved testing the merged model's ability to handle health predictive tasks in a practical scenario, showcasing how it can reason about medical data effectively. For instance, it might analyze symptoms or lab results to provide insights without ever having been trained on individual patient records. Overall, this work builds on previous research in model merging, citing studies like those by Ortiz-Jimenez and others, which have shown that merged models can generalize better across different data and tasks. By applying this to healthcare, the paper positions model merging as a privacy-preserving alternative that doesn't sacrifice effectiveness. The authors emphasize that their best model is publicly available on Hugging Face, allowing other researchers and developers to access and build upon it. In the broader context, the paper highlights how LLMs have revolutionized fields like medicine, with examples such as Metatron, BioBERT, and BioMistral, which were fine-tuned on medical texts. But it also acknowledges the ongoing privacy challenges, referencing reviews and techniques like data sanitization and differentially private training. PatientDx offers a fresh perspective by prioritizing privacy from the outset, potentially paving the way for more ethical AI in healthcare. The authors, including José G. Moreno, Jesus Levan Melgarejo, and others from the University of Toulouse and affiliated institutions, argue that with the right merging strategy, it's possible to create models that outperform their base versions on private data without compromising security. This approach could be extended to other sensitive domains beyond healthcare, where data privacy is paramount.